The components of Kubernetes. Welcome to Audiobook, where we'll explore the essential components that make Kubernetes the powerful container orchestration tool it is. By the end of this audiobook, you'll understand how each piece of the puzzle works together to maintain, schedule, and run your applications across a Kubernetes cluster. Let's start by breaking Kubernetes into two main parts, the control plane components and the node components. These form the backbone of any Kubernetes cluster. Control plane components. The control plane is like the brain of Kubernetes, managing the entire cluster and making decisions about scheduling, scaling, and maintaining the desired state of your applications. Think of it as the command center of the Kubernetes system. Kube API Server, the front door of Kubernetes. The first piece of the control plane is the Kube API Server. You can think of this as the front door to your Kubernetes cluster. Every interaction, whether it's deploying an application, scaling a workload, or making configuration changes, passes through the API server. The API server is responsible for processing all API requests, validating them, and then updating the ATT database, which stores all the state information about the cluster. Essentially, when you tell Kubernetes to do something, it goes through the API server first. ETT, the brain's memory. If the API server is the front door, then EATD is the memory of Kubernetes. It's a distributed, key-value store that holds all the critical information about your cluster. ETT stores the desired state and the current state of your cluster. For example, if you want 3 replicas of a pod running, EATT stores that desired state. It also tracks the actual state, how many replicas are running at the moment. This comparison helps Kubernetes continuously reconcile any differences between the desired and actual state. Kube Controller Manager, the watchful eye. Next up is the Kube Controller Manager, the watchful eye of Kubernetes. It's responsible for constantly watching the state of the cluster and ensuring everything matches the desired state stored in ETG. For example, let's say a node crashes, or a pod fails. The controller manager notices that something is wrong and takes corrective action by creating new pods or redistributing workloads. It manages everything from ensuring the right number of pod replicas are running to managing nodes and network endpoints. Kube Scheduler, the decision maker. Now that we have controllers keeping an eye on things, let's talk about Kube Scheduler, the decision maker in Kubernetes. Whenever a new pod is created, the scheduler decides where that pod should run. It checks the resources and capacity of each node in the cluster and assigns the pod to the best fit node. The scheduler makes sure that the cluster's resources are used efficiently, distributing workloads across nodes to maintain performance and reliability. Cloud Controller Manager, connecting to the cloud. The Cloud Controller Manager allows Kubernetes to interact with your cloud provider's infrastructure. Whether you're running on AWS, Google Cloud, Azure, or any other cloud, this component manages things like cloud-native load balancers, volume management, and network routes. This separation allows Kubernetes to work smoothly across multiple cloud environments. Node components. Now that we've covered the control plane, let's move to the node components. These are the workers that actually run your application containers. If the control plane is the brain of Kubernetes, then the nodes are the hands doing the work. Each node in the cluster runs a set of key components that manage the execution of containers. Kubelet, the node agent. First, we have Kubelet, the node agent. The kubelet runs on each node and makes sure that containers are running according to the instructions from the control plane. When the API server tells the kubelet, I need 3 pods running on this node, the kubelet pulls the container images, starts the containers, and then monitors them. If any of the containers fail, the kubelet will restart them, keeping your applications running smoothly. Kube Proxy, the traffic controller. Next is Kube Proxy, which acts as the traffic controller of Kubernetes networking. It ensures that network traffic reaches the right pods by setting up network rules on each node. For example, if a user or another pod tries to reach a service, Kube Proxy directs that traffic to the correct pod, even if the pod moves to a different node. It handles all the load balancing and traffic routing, making sure communication within and outside the cluster happens seamlessly. Container Runtime, the container worker. Finally, we have the container runtime, which is the software that actually runs your containers. Kubernetes supports various container runtimes like Docker, Containered, and CRIO. The container runtime pulls container images from a registry, creates containers from those images, and ensures they run in isolation. It's responsible for the execution environment of your application containers. Additional concepts and components. Now that we've covered the core components, let's talk briefly about some additional key concepts that help Kubernetes work smoothly. Pods, the basic unit of deployment. A pod is the smallest deployable unit in Kubernetes. It represents a single instance of a running process in your cluster. While most pods contain just one container, some can run multiple tightly coupled containers. Pods share the same storage and network, allowing the containers to work together. Services, stable networking for pods. A service in Kubernetes provides a stable endpoint for accessing pods. Pods come and go, but services ensure that other parts of your application or external users can consistently connect to your application, even as pods change. Deployments, managing pods at scale. A deployment allows you to manage and scale pods easily. Deployments handle tasks like rolling out new versions of your application or scaling the number of replicas up or down, all while ensuring that there's no downtime. You can also roll back to a previous version if something goes wrong. Namespaces, logical isolation. Namespaces provide logical separation within a Kubernetes cluster. This is especially useful when different teams or projects share the same cluster. Namespaces ensure that resources like pods, services, and deployments are organized and isolated from each other. Config maps and secrets. Config maps store configuration data that your applications need, things like environment variables or configuration files. Secrets store sensitive data like passwords, API keys, or certificates. Secrets are encrypted, ensuring that sensitive information stays secure. RBAC, role-based access control. Finally, role-based access control, or RBAC, is Kubernetes' way of controlling who can access and perform actions on resources in your cluster. You can define roles with specific permissions and then bind those roles to users, groups, or service accounts to enforce security. What is a Kubernetes deployment? Imagine you're managing an application that needs to be consistently available, scalable, and easy to update. Kubernetes deployments are your tool for achieving this. A deployment is a declarative way to describe the desired state of your application, such as the number of instances, replicas, you want running, the version of the container image to use, and how updates should be handled. Kubernetes takes this description and ensures your cluster matches it. It's the backbone of managing your application lifecycle in Kubernetes, allowing you to perform rolling updates, rollbacks, and scaling with ease. Why use deployments? Picture this: your application is growing, and you need a system to handle change. Deployments address key use cases, including scaling applications. Automatically scale the number of replicas up or down based on load. Rolling updates. Seamlessly update your application without downtime, rolling out changes incrementally. Version rollbacks. Revert to a previous version if something goes wrong. Self-healing. Automatically replaces failed instances to maintain availability. They act as the middleman between your application's desired state and the actual state of the Kubernetes cluster. The anatomy of a deployment YAML file. Let's dive into the code that brings deployments to life. The YAML file defines the desired state of your application. The basic structure includes such fields: API version, kind, metadata, spec. Breaking down the fields. Every line in the YAML is a cog in the deployment machine. API version indicates the API version of the resource, such as apps/v1. Kind specifies the type of Kubernetes resource, deployment in this case. Metadata provides unique identifiers and labels for the deployment. A unique name for the deployment. Labels, key value pairs for categorization and organization. Is specification of the desired state. Replicas, number of pod replicas to maintain. Selector, criteria for selecting the pods this deployment manages. Match labels, labels used to associate pods with this deployment. Template, blueprint for the pods created by this deployment. Metadata, labels applied to the pods. Spec, configuration for the containers within the pod. Containers, list of containers in the pod. A unique name for the container. Image, the container image, including tag, for example, latest, v1.2.0. Ports exposed by the container. Rolling updates. Kubernetes deployment automatically performs rolling updates by default. You can configure update strategy using strategy and type command. In Kubernetes, the deployment strategy defines how updates to your application are rolled out to the pods. This is crucial for minimizing downtime, ensuring stability, and controlling the risks associated with deploying new versions of your app. Kubernetes provides two primary deployment strategies: rolling update and recreate. Rolling update, default, slow and steady wins the race. With this strategy, updates are applied gradually. Kubernetes replaces pods incrementally, ensuring that a portion of the old version remains running while the new version is deployed. This ensures zero downtime for your application. Key features. Incremental pod replacement ensures at least some replicas are always available. Supports configuring parameters to control the rollout speed. Rolling update field in YAML file includes max surge and max unavailable fields. Max Surge specifies the maximum number of additional pods that can be created during the update. Max Unavailable defines the maximum number of pods that can be unavailable during the update. For example, if you have 3 replicas, setting max surge equals 1 allows Kubernetes to create up to 4 pods during the update. Setting max unavailable equals 1 ensures at least 2 pods remain available at all times. Recreate strategy. Out with the old, in with the new. This strategy stops all existing pods before creating new ones. It's simpler but can cause downtime because the application is unavailable during the transition. Use cases. Applications that don't need high availability. Scenarios where rolling updates are impractical, for example, database schema changes that require all instances to restart. Advanced strategies. Kubernetes also integrates with external tools like Argo CD, Spinnaker, or Custom Logic for more advanced deployment strategies, such as blue-green deployment. 2 environments, blue and green, are maintained. The new version is deployed to the green environment, tested, and then traffic is switched from blue to green. Ensures zero downtime. Allows thorough testing before switching traffic. Note: Kubernetes doesn't natively support blue-green deployments, but they can be implemented using tools like Istio or custom scripts. Canary deployment. A small percentage of users are routed to the new version initially. If the deployment is successful, traffic gradually increases until the new version is fully adopted. Minimizes risk by testing on a subset of users. Tools like Istio, Linkerd, or Traefik can help implement this. Choosing the right strategy. Rolling update. Default choice for most applications, balancing availability and ease of deployment. Recreate. Use when downtime is acceptable or unavoidable. Blue-green/canary. Ideal for critical applications where downtime or errors have high impact. Environment variables. Pass configuration values to containers using name and value fields. Resource limits. Manage CPU and memory usage using resources field, which includes requests and limits subfields. From code to deployment, Kubernetes brings it all together. A Kubernetes deployment YAML file is your roadmap to managing containerized applications at scale. It's concise, powerful, and automates the complex tasks of application management. Armed with this knowledge, you're ready to explore the vast world of Kubernetes and build resilient, scalable systems. Conclusion. Putting it all together. To summarize, Kubernetes is a well-orchestrated system of components that work together to manage your containerized applications. The control plane, with components like the API server, EATC, controllers, and the scheduler, manages the overall cluster. The node components, such as the kubelet, kubeproxy, and container runtime, execute the workloads and keep everything running smoothly. These components, working in harmony, provide the power to deploy, scale, and manage applications in a dynamic, distributed environment. Kubernetes abstracts away the complexity of managing containers at scale, allowing developers and operations teams to focus on building and running applications rather than worrying about infrastructure.